Hi, my name is John Watson, and this is SNHU's Computer Science 260 Lesson 6, covering binary search trees. As before, we start by taking a look at the requirements, which you'll find here in this labs files. When we first download that, open it up, you'll find a instructions document. And so for Lab 6, we're going to use our familiar data files for test data. We've got a full collection of online auctions or bids for auction, an auction site. We've also got a smaller subset with just about 180 bids in it for 1 month. And again, we're focusing on binary search trees. We give you a sample starter program, which I'll take a look at in a moment. And for this, we're just using console I/O. The focus is not on being pretty, but on the algorithms and the data structures involved. So our menu system this week is going to be loading bids, displaying all bids, find a bid, and that's really where we're going to spend a big focus of the time, is searching the binary tree. And we give you, as I said, a starter program. And we ask that you set up your Eclipse environment. So let's take a quick look at what we have here. So we've got Eclipse. Now I've already downloaded the lab files, expanded them, and started the sample project. As before, we set the compiler settings to C++ standard version 11. And if we take a look at this program, you can see we've got a binary search tree class already defined. We've got a node pointer to a node, which we call root. We've got some private methods and some public methods. Going back and looking at the materials, we'll see that our first order of business is to define some structures for our node and some housekeeping variables. And in Eclipse, we've got some fix-me notations in here. So the first one is to define our internal structure for the tree node. And so for that, we're also using our Zybooks reference as a guide, chapter 6, where we look at binary search trees and the searching algorithms. Let's take a quick peek at that. One of the concepts of a tree is that there's a root node, or the topmost node, and then there are additional leaf nodes, and then you've got a height property, which is the number of nodes down to traverse to get to the bottom, which in this case it's got a height of 3. One of the key facets or concepts of a binary search tree is that the tree is stored in ordered fashion. So searching and the search algorithm can be very, very fast, but it comes with a little bit of a price in that you need to spend some time when you're building a tree, making sure that you maintain the order. And the notion of a binary search tree is that the ordering is from left to right. So from any given node, all the nodes on the left side of the tree are going to be less than whatever current node you're on, and all the nodes to the right are going to be greater than. And so given this mechanism, let's look at what a search would look like. Before we do that, we'll go back and take our first step, which is to define a node. So we've got our bid structure already defined for our eBids. And so we'll start by our node. We'll hold a bid, and we're going to need a node pointer for left and right, which is a key aspect of our tree. Now, like always, when you're working with C++, you want to make sure that you define a default constructor to initialize your variables. And this can trip you up because, unlike other programming languages, we're not always guaranteed the initial value or state of a variable. So when dealing with C and C++, it's usually best to always initialize things. So we're going to, whenever a node is constructed, we're going to set the left node pointer to be a null pointer, and the same for the right. A little further down, one of the things you'll notice is there's already a warning here that if we take a look at this, it's saying that the member root was not initialized. So we've got a node pointer in here within the binary search tree class. So we should do the same for that. Save all this. And let's see what else we have. That takes care of that. So now we've got a node structure, which represents one of these entries. And the nodes contain a bid and a pointer to the left and right subtrees underneath that node. So that gives us our basic structure for working with a binary search tree. The next step is to implement inserting. And notice we have marked this with parts 2A and 2B. There's a public method called insert, which takes a bid. And if we go back to the definition, you can see right here, we've got an insert, but we also have an add node private method, which takes a node and a bid. So let's look at this in a little more detail. And again, you can see examples of doing this. Let's see, we have an add, yes, we have an insert here. So let's take a look at that. The basic logic you can see here, if tree root is 0, then we assign the current node that we're passed to it, and we make sure that the left and rights are already initialized. Else, we start basically iterating through. Now, there's two ways you can iterate through a search or a collection of nodes. One is a while loop, and another would be with a recursive call. I'm going to implement it with a recursive call because that's the way that we've intended this to be, is that if you look at add node, it's if nothing else, it's defined as, or has a comment to add a bid to some node somewhere in the tree, and it's recursive. So we'll come back to that in a moment, but let's go back and look at this. One thing I want to point out that people may have seen or noticed is that you're seeing values of 0 when you're comparing pointers. This is a leftover of the C roots, where technically a null pointer and the capitalized NULL constant was a 0. I prefer to use the C++ more descriptive null PTR, null pointer. So you're going to find me doing that. And while they're both technically right, I would encourage you to use the method that supports the newer style syntax and is more readable and more understandable. So basically, if we were to do what we saw, let's see, in here, I'm going to put this over here. Actually, let's get fancy. You should be able to see this. If we want to implement this here, we just say basically, and remember the binary tree itself has a root node, which defines the top of the tree. So maybe I can squeeze over just a little bit. So when inserting, we're going to start by checking to see if the root equals null pointer, which means there's nothing in the tree. Then simply assign the root to be a new node constructed from the bid. Now, when I do this, we're going to see that there are no options. There's a node address and an empty default constructor. So what we can do to improve this would be we're going to go back and create a second constructor that we initialize with a bid. That'll just make our syntax a little easier. So again, a constructor is simply the class or struct name followed by normally parentheses, but we're going to enhance this by passing in a bid, which we'll call a bid. In this case, we're going to do one more syntactic trick, which is to put this syntax here. So when we're calling this constructor, the colon, and then you can follow it by another constructor, and it will be called. So in essence, when we construct a node by giving it a bid, the first thing it will do is call the default constructor with no arguments. That's going to cause left and right to be initialized. And then all we need to do is assign our bid structure And you could also do this. Because reference to this dot bid, because this is a reference to the current instance. So if you wanted to be fancy, you could say, oops, gosh, I have all kinds of trouble with my keyboard. Bid equals a bid. So there, we've gone and constructed a node with the bid. So now back to the insert, we can say node equals new node, and now when I do control space, you notice one of the options is a bid. So now I've got a different constructor that I can use, and that allows me to simply do this. I construct a node by passing it the bid. I've written the code once up above in the node constructor to do all the assignment and setup work, and at this point, we're done. Now, what happens if the node or the root node is not null if there is a existing node? And that would be a case for an else condition. Now we're going to do this add node. And the starting node will be the root. And we're going to pass to add node the bid. And this is based on what you were given. And I think I made a comment in somebody's, or perhaps a confusing classes, but what we did here was provide you a lot of boilerplate code, so you did not have to worry about that. You could just focus on the algorithms. But that also implies that you need to work within the constraints of the code you were given. By that I mean you can't just start basically slinging code and doing what you want. There was a design intention that's implied in that, and we've got an add node, and the add node is, at least through comments, is mentioned as being recursive. So the idea would be you'd hopefully follow that behavior and do what was needed. So that comes to 2b, which is now that I'm going to pass it in. So remember, we're calling this starting at the top of the tree, passing it the root node. And that really refers to this code here you're seeing over on this diagram. When we add a new node in this manner, we basically need to start comparing and looking at and going down the tree. For simplicity's sake, I'm going to start by just providing an implementation within our world for that. And we can begin by saying, first off, if this node's, so we were given a node which starts with the root node, if this node's bid.bid ID, pair bid ID, if that comparison is greater than 0, what we're asking here is if the new node is larger than this one. If that's true, then we're going to make this node one on the left. Let's see, did I get all my parens right? Gosh, sorry about that. I spent too much time switching operating systems and versions. So here we can say something simple. Actually, let me put a note here. We'll say add to left subtree. And we'll eventually get down to, let's do this, and I'm going to do it this way. Else we'll come back to that. Now, one thing you have to be careful of is, remember, we're passing in the root node to start. We want to ensure that that root node may not have any children. So the next thing we need to do is look and see if this node left pointer is null. Then, if true, then we need a new node constructed that becomes the left pointer. And that's actually pretty easy. We just say node left equals new node bid using that nice constructor we built. So again, I'll just step back to follow through. If the root is null, then we create a new node that becomes the root. Else, we're going to add a node to the root given the bid. And then we go down to here and we say if the node is larger than the bid's ID, then we start down the left. And then we go to the left side and we're saying if this left pointer is null, then we construct a new node and make it the left pointer. Else, and here's where it gets interesting. That means if this is not the left, let's see if I can quickly find an example of that. Oh, I guess we'll just use this one because it's quicker. Do that over here. So in the case that the left node is not null, then we need to basically keep traversing down. Only now we're going to call add node again, giving it the current node we have, which is root, its left pointer. And of course, we keep passing the bid along. So again, I'll repeat, we start with the root. If the bid value is less than the nodes, then we go to the left. If there's no left, then we create a node and make it the left. If there is a node, then we need to traverse down. And so this short little add node routine can basically traverse down from a node anywhere down the tree to the bottom looking to add it. And that's basically it. You've got the work done for the left side. Now for the right side, it's really basically the same thing. So I'm going to save myself a little time in typing and paste this in, and we'll change this from left to right. Assuming I can type. Let's see, so if the right node is null, we make the right node a new node. Else, we add by going down the right side of the subtree. And that's it. We're just going to keep traversing down, and we've now implemented a search. Let's see where we're at here. Excuse me, we've implemented an insert. But if you want to go back and look at searching, that becomes a little more interesting. Now we can do the same thing. Go back to the search here. We could use a while loop, we could use a recursive. I think for the search, I'm just going to use a while loop to give you a difference. To start with, when you're searching, the search, they call it tree search, but they start by making the root node the current node pointer. So we start at the top. So we just say, we have a node instance we'll call current, a node pointer rather, and we're going to assign root to it. So we begin there. And then the rest of the way is, and I should do this. Gosh. So we start with a simple while loop, and we say while current is not equal to null pointer, which just means we have something. And then first thing we do is we determine if we got a match, because this current node might be the one that matches. If, and this gets a little messy, but current bid ID dot compare that to the bid we were passed in, which is just plain old bid ID. and we say if that equals 0, then the comparison was a match. Then we simply return. And notice our return type is a bid, so we're going to return the current node's bid. And that's it. We found a match, and we return that bid. Otherwise, we hit the condition where it's not. And this, again, follows the basic semantics of a binary search tree. So if if bid is smaller than current, then traverse left. And so let's code that. If our bid ID compare, we're going to compare this to current. I'm doing it the other way, but that's okay. Current bid ID. And we're going to say if it's less than 0, that means that the left-hand argument is smaller. If it's less than 0, then we're going to say current equals current left. And this way, so as we're looking at it, we're saying if current is less, then we're going to make this left pointer, let's say we started here, we're going to make the left pointer the new current load. So basically this while loop is just going to keep working its way down. Let's take a look at that and see what's going on. Else, it's larger, so we're going to want to set current equal to current right. And that's essentially the search. If we drop out of the while loop, that means we traversed one side or the other all the way to the end, and we did not find a match. In this case, since the search method is designed to return a bid, we're just going to create a bid instance and return an initialized empty, nothing there bid. Oh, I know what I did wrong. I think it was here. Current bid. Yeah. And that takes care of implementing a search. We've coded the insert. We've coded the search as well as the recursive functions. And now let's take a look at our old friend main. Main is set up to take 0, 1, or 2 arguments. If you pass no arguments, then we'll default to the monthly sales and we'll use a search key for 98109. If you pass 1 argument, which is the path, if you wanted to say we use the large file, then we'll default to this, or you could pass both. So now that I've got a good compile, I look here, I look here, there's a debug, there's our compiled executable, and I go down to here, take a look, we could see that. So if I want to run this, I just type lab and the tab key, and there's our menu load bids display. Oh, we'll do a load first, and there they are, 16 clock ticks. Might as well do a display. Oh, I didn't implement display. That's okay, but we're going to do find bid, and if life is good, we should come back with 98 or 109, which they're not sorted in order. So let's do this. The old Excel trick. We'll go to data, filter, and the value was 98109. We can see right there, Whirlpool wash and dryer, $225. So let's see how we do. Oops. Let's see how we do. I'm going to choose 3, and there it is, 98109 Whirlpool washer. Notice it took 0 clock ticks. Gosh, where am I at? Here we go. We've got our inserts, we've got our search, and let's take a look at what removing a bid would be. Of course, the remove is similar to what we did for the insert. We're going to start by simply, notice it's a 4A, there should be a 4B there, because we don't have. Somehow they got dropped off. There is a private method called remove node. There it is. But we don't have a add node. Huh. It's okay. We'll put that in. Let's start with remove. The intention was to do something similar to the add. Let's get on to where add is. There's add. There's in order, which we'll come back to. Well, it seems like some lines are missing. And when you remove a node, I believe we're just going to return a void. So we'll say void and I think we'll take now we're going to want a node pointer. What do we use here? Just node. Let's see. Node pointer. Oh, we're going to remove a node pointer. Now the format looks the same. Removing is a little trickier because you have to readjust the tree. So in this example, we're looking for 25 and it wasn't found. As you can see from here, the concept becomes a little bit more interesting. We start at the top and we work our way through. So using the previous model, we're going to start by calling our public method, and we're just going to say this, remove, and we're going to start at the root, and we're going to pass the bid ID that we were given to call. Now, going down to the remove, we begin by setting the current to the root, or the root to the current we were given, and start our work. So the first thing to know is if we're starting on an empty tree, this is a little safety thing. We're going to say if node is null, turn node, because we need to return the node pointer. Next, we're going to see if we need to go down the left node, left subtree rather. Node bid ID. If the string bid that we're given is larger than, actually left we're going to do, is smaller than the bid, in the current node, which starts out at the root. Then we're going to go down the left side. So to do that, just like we did for the add, we're going to say node move node, and we'll keep working our way down. Now we'll get interesting in a moment. And this is going to be an else. We're going to say, yeah, same thing, but the other way. Copy this, and we'll say node right. So this will allow it to recurse down either the left or right side, depending on what we're given. Now, we get to the case where I think we took care of left and right. Yeah, we're going to work on this where we find a leaf node. To do that, we're going to say this less, else. It needs to be an if. There we go. So the idea is if it's less than, if the node is smaller than the bid, we're going to go down the left side. If it's larger than, we're going to go down the right side. Otherwise, we're on a node that needs to be removed. And then now we get really tricky. We have to take the case of no children. So if that's a leaf node that has no children, and that's just a fairly simple test. If this node's left is null, and this node's right is null, then we simply need to delete this node and let's see. There's no children. Delete it. It's going to make sure it's empty. And then just to be sure, let's just initialize it to null pointer. Now, we get into some fancier things. We have to look for different cases. Looking at the tree structures, you could be in a situation where you're here, there's one right child, or this node, there's two children. As we go down here, here's a node that has two children. Here's a node that has two children. So we have to treat all these conditions. And for that, we're going to say, oops. Pointer and node right equals a null pointer. Then we need to swap these out. So if there's a child on the left and none on the right, then we want to delete the right node, leaving the one attached. So we're going to need a temporary node pointer to hold this. We're going to say node we've made a copy of the node pointer to temp. Then we're going to say This node now equals the right node. And we'll just delete the temp. So if we don't have a left, but we do have a right, which I don't see a case illustrated here. Let's assume that wasn't there. If we don't have a left and we do have a right, then we're going to make a copy of this. We're going to set the node, which is a pointer we were given. We're going to set the node equal to this, the right one, and then we get rid of the temp. So what we did was we made a copy of this pointer here. We set the node to point to this. So now this node pointer is going to point to the right child down underneath this one we're examining, and then we can delete this one. So now this node will point to here. So we've eliminated a case of a subnode with one to the right and none to the left. And you got to do the same for the other side. I'll start by copying this. This is going to be an else if, one child to the right. If, save a little time. If the right is not null and the left is null, then again we make a copy, only we're going to say node right. Actually, it's wrong. There's one child on the left is going to be left. There's one child on the right. We're going to take the right one. Delete temp, and we're done. Now we have two children, which comes and this is just going to be an else. This one becomes a little trickier. Find the successor, leftmost child of the right subtree. Find the successor, the leftmost child of the right subtree. So we're going to say, let's see, we need a node pointer again. We're going to temporarily point to the right side and then use this temp to look at the left. We're going to keep finding the left side to look for the minimum. Hey, what am I missing? Oh, there we go. Get over here. So if we get two children, we're going to temporarily point to the right side. And as long as there's none there, we're going to keep going until we find the minimum one, and we're going to bring that right node up. So there's our while loop to do that. So then now this node, which we hung on to, we used the temp to go down the right side and find the one we're getting rid of. We're going to say node did. So we hung onto that pointer. We're now going to copy the bid to it that we hung on to. And then we get rid of that one to the right. At the end of it all, we're going to return the node that we were working on as we fall through. So we have a good compile. Let's see if we can do this. Actually, let's take a look at the main and see what we do for remove. Search with big key, remove. That's correct now. Load the bids. Are loaded. Do a find. We find 98103. Excuse me, 109. We remove a bid. And then we try to find that same bid again. And it says bid ID not found. And so there we go. So again, the remove is a lot more interesting. Start at the root. It's just in case it's empty, we just return. If the value we're comparing is less than the current node, then we traverse down the left by calling remove recursively. So we're basically walking down the tree until we find somewhere where it's neither less than or greater than, or in other words, it's a match. And once we find a match, then we need to handle that. In this case, we handle the case of a leaf node at the bottom. We don't have anything, then we have 2 children to deal with. So now we have to, so this is a case like here for 30, I've got a node that's got 2 children. And so I start by grabbing the right pointer, removing that guy, because remember that the way the BST works is the ordering should be less than or equal to. Come on, Cybooks. I think they showed it in one of the examples here. If this ever comes back, I'm sure you, there we go, less than or equal to. So here, we grab the right node, we start going down the left till we get to the end of that, and then we pull that up is basically what we're doing. We take the node, we grab that left node and we store it. We store the bid for that left node. And then for the right side, we go down and remove it. So we're basically pulling up the missing entry, which we can see here. We're going to pull up an entry by removing a node in the middle. That's what becomes challenging. And so here we've got the implementation using recursion, whereas I believe the book's implementation chose to do it all with while loops. The important thing is that we have a pretty full implementation of a binary search tree. We could also do the in order, which I don't think I did, but if you wanted to traverse the node in order or the tree in order, it's pretty straightforward. Let's see what we can do. If you want to traverse, in order traversal. As always, we start in the public tree class by calling in order, giving it root. That's not very interesting. And when we call the in order one, remember that the in order traversal is visit all nodes left to right. So in order to implement that, see, here we are. Start by, once again, being safe. It's really pretty easy. We say node left. And then you go down the right side, we could say node in order. Node right. Now there's one more thing we want to do. So we've done the left and the right node, but we haven't handled the current node. Where's my print? And we'll just borrow this. Because you're going down the left side, go down the right side, we mustn't forget the one in the middle. And all we need is a little bit of dereferencing. And we could even get cute if we wanted to and do something like this and make it even. Doesn't really matter. So if we're going to traverse in order, given starting at the node, at the root, you go down the left way, all the way to the bottom, and you keep calling it recursively. And as you hit a node, you print it out. So do I have an in order? I don't know if I do or not. Display all bits too. Ah, that was our in order. Compile it, and we'll make sure we use a small file here. Load them, display. And we just zip through by calling recursively in order, which, oops, starts at the root and calls into the recursive method. And this guy hits the left, hits the right, excuse me, prints the center node and then prints the right. So it's going to print all the way down the bottom, and as it comes back up, it'll print the right, that node and the right side. Then it'll come back up, print that node and the right side. And this way you traverse the entire tree in order. And you notice when we look at this printing, you'll find that, let's see if we can find the Excel file. If you remember correctly, these are not in order. 9, 9, 9, 8s, 9, 7s, 9, 8s, 9, 7s, 9, 8s, and yet when we look at here, we see that they are indeed listed in order. And that's it for this exercise. Thank you.